Hello, welcome to another seminar of the Astronomy Department seminars. Many thanks to joining us here in the Google Meet, and also if you are following us through our YouTube channel. It is a pleasure today to have with us Professor Bruno Sicardy. Many thanks, Professor, for accepting the invitation and being here with us, sharing your work. Bruno Sicardy got his PhD degree from the University of Paris, and he made several discoveries in the field of planetary science, such as the discovery of the incomplete Neptune's rings arcs, among others. And currently, he's a professor at the Université Pierre and Marie Curie, and researcher at the Observatoire of Paris. He devotes most of his work to the observation and study of the dynamics of planetary rings and atmospheres, and as well as the dynamics of protoplanetary disks. And today he will talk about the rich harvest of stellar occultations, rings, atmospheres, and other traits. And before we start, I will ask you, please, everyone, to turn off your microphones and your cameras during the talk. And if you have a question, you can ask the question during the talk or after the talk. So if you have one, you can indicate this with the hand in the Google Meet, or you can write it down in the YouTube chat. So Professor, whenever you're ready, you can start sharing.
Okay, good afternoon, everybody. Thank you for inviting me. So I will share my presentation with you. Okay. So, can you see it, everybody?
Yes.
Okay, so I will use my laser now. Okay, so I will have a presentation on stellar occultations and their application to the study of the solar system. It's part of a European project called ERC. It's a European Research Council, which gives money and support and postdocs equipment for 5 years. So it's basically and mainly recent results obtained within the framework of this European Research Council project called Lucky Star. So this project is presented. So if you type in Google or other browsers, Lucky Star Project ERC, you can go to that page, which explains what I am doing, and you have several tabs here to give the results, the publications, presenting the team, and also prediction, which is a tool for observers, both professional and amateurs, to observe, plan and observe occultations, and also some ephemeris part. And okay, so that's different things that you can learn about my project in that page. Here the Paris Observatory group in Meudon, which is part of Paris Observatory outside Paris, just in Meudon. So postdocs, PhDs, engineers, senior scientists, young scientists. Some of these people are back to Brazil now, but stayed at some point with me in Paris during this project. So it's a collaboration with other groups in the world. So one group is the so-called Rio group, even though all the people are not from Rio. So in Observatoire Nacional do Rio de Janeiro, both with researchers and PhD and postdocs, also from Gorantigueta and Valongo and Observatoire Nacional. And another and third group I'm working with closely is from Granada in Spain. It's led by José Luis Ortiz. And it has some postdocs and senior scientists and also PhD students. So, I mean, in between the Meudon group and Rio group and Granada group, we are organizing and planning and analyzing and publishing results of our different campaigns. So beside this, which is sketched in this map, so Paris, Granada, Rio, there is a amateur group called International Occultation Timing Association, is IOTA in Europe, which is very active in participating to campaigns with us and providing a lot of results. So we have other dots on this map, and they come from other amateurs worldwide I'm working with, especially from Australia, New Zealand, Japan, some of them from Brazil, United States, and it's a mixture actually of amateurs and professional. So it's kind of unique in that sense that it's participation of a large amateur community to those observations. And I estimate that I interact with something like 200 people in the world, most of them amateurs. And they are very good cameras, equipment, and they can provide high quality data. So it's not just for fun and observe from time to time, but really participate to campaigns and provide high quality data sets. So the Lucky Star project was rather timely, especially because it came right after the discovery of a ring of rings around a small object which is orbiting between Uranus and Saturn called Chariklo. And the big surprise, it was discovered partly by a Brazilian team from Chile. And this small body called Chariklo is about 250 kilometers across. It's a big asteroid. And for our surprise, we discovered that it is surrounded by a disk, a ring, better say, a very narrow and dense ring. And a few years later, there was another ring discovered around Haumea, which is a dwarf planet, which is much farther away. It's much farther away than Pluto from the sun, and it's pretty big. I mean, Haumea is, as I'll show you later, it's almost as big as Pluto, and it is also surrounded by a narrow ring, which was another surprise. And this project was developed in the framework, in the, let's say, the advent of a big European Space Agency mission called Gaia, which is measuring millions or billions of stars, giving very accurate position for them. And those positions were really key to have nice and accurate predictions for our occultation. And then it boosted actually the project because it provided a much higher success rate. Another interesting event during this project was a flyby of Pluto by the New Horizons NASA mission in 2015, which returned a lot of results on Pluto's surface, but also on its atmosphere that I've been studying and analyzing and observing by stellar occultation well before the encounter. So here you have the detection, the number of occultation observed by per year. This is a plot available on that site in Curitiba. It's maintained by Felipe Braga Ribas in Curitiba, and it gives a number of events of occultation observed per year. And you see a big jump here of events, especially since the release of the data release catalog by Gaia #2, which gave accuracies of about 1 milli-arcsec for millions and millions of stars. And then the success rate of our occultations were just exploded because of these new Gaia catalogs. So it's a new era in that sense that before it was pretty difficult to observe occultation, and now it's kind of easy. Easy meaning that we can actually consider many more objects that we were considering before. So before, the main difficulty was that those objects like Quoaar or Pluto or Eris, they are trans-Neptunian objects, and they are represented here not in real size but in angular size. So Eris, for instance, is as large as Pluto, but is it farther away so that it appears smaller. And it gives you an idea here of the size of those objects, which is about its stamp observed at a distance of about 150 kilometers. And before, the accuracy of the prediction was about the size of Pluto. Before, I mean, 6-7 years ago, it was the size of Pluto Charon. So the probability to get the occultation to see the bodies passing in front of a star was less than 50%. So now the accuracy reached by Gaia is 1 milli-arcsec, which is typically the size of the indentation of a stamp. So we went from something which was very uncertain, so we didn't know if we could observe an occultation by Quotations, for instance, to an accuracy which is within the indentation of the stamp, which means that we can now choose the place where we want to observe the occultation, like this side of Pluto, that side of Pluto, etc. And to give you an idea, this is the angular resolution that will be obtained by the extremely large telescopes, European in Chile, in some years from now, which will be about 6 milli-arcseconds. So here's an example of an occultation observed from northern Chile by a smallish telescope in San Pedro, by Atacama, by Alain Maury. And it lasted for about 1 minute, so it's a bit accelerated here. And you can see here the star disappearing behind Quotations, which is a dwarf planet. And you don't see Quotations because it's too faint. It's a very small object far away, so it's not detectable in these images, but the star is detectable, and then it's not detectable. So from the duration of this event, we can assess or reconstruct the shape and the size of the body. Characteristic of this is those occultation has been observed with a very broad range of instruments. So here's an example of place we observed from in 2011, I think, or 10. It was an occultation by Varda, a trans-Neptunian object, and it was observed essentially at 0 meter altitude, somewhere at the seaside with a very small, extremely small telescopes. 12 centimeters. In other instances, we use portable telescopes. This is one that was deployed in Namibia, in Africa. And this is a 50 centimeter telescope. So we can carry that around in the car and then put a camera, attach camera to it, and then record everything on the laptop. And at the other end, we have very big telescope that you have been using. This one is a 10-meter telescope in the Canary Island that you have been using for stellar occultation. So we can observe from very small to very big telescope, from amateur to professional. This is a plot showing as a function of semi-major axis, which is essentially the distance to the sun. And here the inclination of that object, of the object with respect to the average solar system plane. And all the dots, each dot is actually a particular body that you observe. This one is, for instance, Aries. Here somewhere there must be Pluto and a whole bunch of bodies called the Plutinos are in resonance with Neptune, 3-2 resonance. And here you have a big accumulation of body than the Trojan asteroids, which are sharing the orbit of Jupiter, and you have been observing more and more occultation by those bodies in the recent years. And as of today, actually, we have been observing more than 90 different bodies by occultation, with 36 trans-Neptunian objects. So Neptune is around here. Centaurs are those objects orbiting between Jupiter and Uranus. Dwarf planets, meaning Pluto or Aries or Quotations, so they're big enough to assume a regular shape. And the Trojans are here, so sharing Jupiter's orbit, and also satellites of giant planets. And here is a few example of objects that you have been observing. So all the green marks are objects observed within the lucky star umbrella. which is my project, and the red tick marks are for other groups in the world. So it illustrates the fact that we are actually leaders now in the terms of number of occultation observed and also number of objects detected and analyzed. So it's a very big project, and it's unique in the world in terms of, you know, variety and number of bodies observed. So we are interested in bodies in the trans-Neptunian region here. So this is the sun in the center. This disk is a lot of objects beyond Neptune, called the trans-Neptunian objects, or the Kuiper belt objects, or the Edgeworth Kuiper belt objects, whatever. And then at some point, these objects are contained in a big sphere, which is the real limit of the solar system, called the Oort cloud, which is at about 50,000 astronomical units, which is a bit less than 1 light year. So beyond that, it's the interstellar medium. And so we have been observing, this is a sketch of the solar system with the giant planets here, and the Neptune is here, and the objects you have been interested in are mainly in that trans-Neptunian region, and some of them are in the, Centaur region, that is near the giant planets. And it's a very complicated region because all those objects have been perturbed by the giant planets, especially in the primordial stage of the solar system, where it is thought that the giant planet interacted between each other, and there are some kind of migration. So Jupiter migrating inward and the other planets outward. And during this migration, there was a lot of interaction between this giant planet and the small bodies. So some of them were ejected, some of them were captured as Trojans, sharing Jupiter's orbit or possibly Neptune's orbit. So my message here is that it's not a static population. The small bodies are moving around. And if you consider, for instance, the Centaur's object, they are on highly unstable orbits, so they don't stay much here. So the Centaurs we do see now here will be gone in 10 million years from now. So this occultation have provided a lot of scientific results since, the 70s or the 80s, and there's a very high ratio to science, very high ratio science over time, because it doesn't take long to observe occultation, a few minutes or 1 hour maximum, but the scientific return is very high. So here's an example of the discovery of Neptune incomplete rings called arcs around Neptune in 84, so published in Nature. This is the measurement of Neptune oblateness using stellar occultation later. Search for more matter on Uranus and Neptune. The probing of Titan's atmosphere by stellar occultation. So the first probing well before the Cassini mission in 2005. This is again in Nature, the measurement of a big variation in Pluto's atmosphere in the last few decades, and then the size of its satellites, Charon, the diameter, the size of another dwarf planet, Eris, which is as big as Pluto. Makemake, also the measurement of its size, the discovery of rings around the Chariklo Centaur, and then another ring discovery around the dwarf planet Haumea a few years later, and more theoretical things published recently in Nature Astronomy related to the dynamic of rings around small bodies, like Chariklo or Haumea. So the first result of stellar occultation is, as you have several observers, this is an example of Titania Occultation, which Titania is Uranus' main satellite. And by placing people on Earth, mostly amateurs, each of them measuring the time of disappearance of the star, make possible to reconstruct the shape. And you can see the outline of the shape of Titania here at very high accuracy. And also you see a displacement between what was actually observed and what was predicted on the left here. And this displacement illustrates one of the byproducts of stellar occultation. So besides giving the size with very high accuracy, it also gives a position in the sky. And especially since the Gaia catalog was released, it allows very high accuracy in the ephemeris of the body. Here, Titania, then a big improvement of the orbital elements and the future, future occultations, or even small effect on the orbital elements of the body. And here in pink, you have our measurement of Titania radius with the error bar, which is the pink region of that rectangle here. And this is a scan by Voyager in '86, showing the topographic features along the limb of Titania, the edge you see of the sky. And this is just to illustrate that we retrieved actually the radius of Titania. 0 is a nominal radius derived from the Voyager images. And here you see the fluctuations caused by mountains and craters. But just this illustrates the amazing capacity of stellar occultation from Earth to have a very accurate measurement of radius. And most of the dispersion, the scatter of the point that we got at that time, were not due to errors in the method or in the timing or in the observations, but were caused actually by topographic features. Another interesting return of stellar occultation is that they can give very accurate shape for irregular bodies. This is here Antiope, it's a double asteroid. So not only you can, so each colored line here is one observer. And then by timing the disappearance of the star, you can clearly see one object here and another object there. And again, it's a very powerful way to have a very high, you see here, very high resolution and very fine resolution, which is a few kilometers in terms of accuracy and details. And this is just impossible to get through imaging. So just to summarize, this spatial resolution obtained during the occultation is a fraction of kilometer. We can detect atmospheres. I will illustrate now at a few nanobar level. So it's very low threshold of detection. And also here I will illustrate the amazing accuracy of the Gaia catalog. So this is a prediction of an occultation with a shadow of Chariklo on Chile, Argentina, and to the right, Brazil. And the blue lines are the shadow of the rings around Chariklo. And before Gaia, the accuracy of those predictions was something like 500 or 1,000 kilometers. So we didn't know if the shadow would come over this telescope here or farther north in Peru or farther south in Patagonia. But then the accuracy of Gaia is such that now we can pin down the accuracy of the prediction to about 1 milli-arcsec, which corresponds to about 10 kilometers. So we went from events which were very uncertain. So we knew the continent, but not necessarily the country. But now we can know not only the country, but the village where it will go. And we also ask for some people to move a bit around to detect some specific features. So we can ask this guy to move down by 10 kilometers, this one to go up by 5 kilometers. So it completely changed the scale of accuracy and the planning of all those observations. And if you compare that with other instruments like the Hubble Space Telescope or the Sphere adaptive optics camera at the Very Large Telescope in Chile, or even the James Webb Space Telescope to be launched this year. These are the sizes of their pixel as projected in the sky at the level of Chariklo or Haumea. So even with the best you can do from the ground or from Hubble, you see that the pixel is much larger than the size width of the rings, and it barely resolves actually Chariklo or Haumea. So you have a few pixels across both objects, but you have no details whatsoever. And even the future ELT in Chile will give only a few pixels across Chariklo or Haumea. So we'll have some idea of the shape or the size, but not very accurate. Now, if you use stellar occultation, we can not only pin down the size by observing the size and shape of those objects, but you can also see features inside the ring here. And all this by using small telescopes. Small, 50 centimeter or even less. So just to illustrate this, this is the best image of Chariklo surroundings. So all this is kind of artificial features goes by the image treatment. And you can see at the center, I put a sketch of Chariklo and its ring. So it's not observed by Hubble. It was put by me here just to show the scale. So Hubble is just unable actually to resolve Chariklo and to image the rings around it. While an occultation, this was observed from South America, from Brazil, Argentina, and Chile, and you can see from various sites and from those countries, you can see the shape of Chariklo being revealed. And if you look at the details of the occultations in each of these cuts here, you can see details inside that narrow ring. So it's a W-shaped, which is interesting per se. It's probably caused by some dynamical effect of confinement in that ring. So just to say here that not only we can resolve Chariklo, but we can also resolve and see some features inside that tiny narrow ring. And because it's observed from different places on Earth, this transformed the Earth as a big observing platform with amateurs and professional mixed up. We can do more. For instance, here, this is an occultation observed from Japan and China, and this cord here observed a strange occultation. So instead of having a clear disappearance of the star, as was observed here from Thailand, there was a gradual disappearance of the star from that place in Yunnan in China. And this gradual disappearance was interpreted as a presence of a canyon, a chasm, okay? Or possibly also another interpretation is a depression. It's a basin caused by a big impact, for instance, on the object. Another example of this topographic feature is from an occultation observed 1 year ago from Europe at different places, mainly amateur. And all the yellow dots are actually positive detections by people who actually detected the occultation, and the blue ones are people who were outside the shadow of that object. And here, for instance, this is from south of France, and you can see that the reappearance of the star was not sharp like here, but it was gradual, and this gradual aspect was caused by actually some features. And when you put everything together, you can first see that the object is not spherical. So there are more than 60 positive quartz, which is really a record for trans-Neptunian objects. It is farther away than Pluto, so it's pretty far away. It's about 40 astronomical units. But an interesting feature here is the depression. So not only we can measure the body, the size and the shape, but we can also detect some topographic features. So this is the ring discovery around Chariklo some years ago, I mean in 2013. So you can see the occultation by Chariklo, and then before and after the occultation by the main body, you have two sharp events, one caused by a dense and narrow ring, and another one caused by a less dense and semi-transparent ring. And this was done from Brazil, Chile, Argentina, and all the observation reconstructed actually the structure and the orbits of this ring. And then there was another detection some years later in 2017 around Haumea. The blue lines are occultation quartz, where the star was observed was disappeared beyond Haumea, which is here, from different stations in Europe. And then the red or green marks here are the disappearance of the star behind something else. And that something else was, that it's not the body itself, of course, but was interpreted as a ring. And an interesting result here is that the orbital period of the particles in that ring, deduced from the mass of Haumea and Kepler's laws, are very close to the 1-to-3 resonance with Haumea, meaning that every time a particle in the ring completes one revolution, Haumea completes 3 rotations. So it's akin to other resonances observed in the solar system between Jupiter, for instance, and asteroids. And I've been working on theoretical works on the evolution of collisional disks. So this is a simple model with no collision, but kind of friction in the gas. So the particle have a friction. So it's describing some kind of dissipation in this disk. And you see that after a while, if you put some topographic feature on at the surface of Chariklo, the resonances will create torques, a coupling between the disk and the body. And this coupling will move particle from the co-rotation, where the particle of the same revolves around the body at the same time as the body completes one revolution. All those particles are going down to the surface of Chariklo, and all the particles outside that co-rotation radius will go away. And so this was a promising result, which was published some years ago. And then and it's akin to the evolution of stars in the galaxy, with resonances between the bulge and the galactic disk. But what's interesting is that recently I've been working with people in Finland, Heikki Salo and colleagues, and they have developed a big collisional code with a much more realistic description of collisions. So you have thousands of colliding particles, and this is Haumea here, and you put a mass anomaly of about 3% of the body here, and in a frame rotating with Chariklo, this is basically the initial conditions. And then after some years, there is a big perturbation of the 1-to-3 resonance on the disk, and after some 16 years, there is a confinement of the ring at the 1-to-3 resonance. So like Haumea, the rings of Chariklo appear close to the 1-to-3 resonance. So I will not enter into the details, but just to say that there are some interesting dynamical problems associated with those narrow rings and the possible confinement caused by resonances between the body and the disk around it. And it is expected that some of the particles are moving down to the equator of Chariklo. There should be a bulge, a ridge, which is a case for Iapetus, which is a Saturnian satellite. And this ridge, in the case of Iapetus, is not well understood, but a possible origin for the ridge is presence of a ring around that satellite, and that ring collapsed onto the equator of Iapetus and formed that ridge, which is encircling the whole body around its equator. And we can possibly sometime not for not for Iapetus, but observed some grazing occultation and try to detect a possible ridge on the equator of Chariklo. Occultation can do other things like measures a shape very accurately. And here's a shape deduced from that occultation that discovered the rings, but also measured the size of Haumea very accurately. And it's pretty bigger than previously thought by indirect methods. And the density that was derived from this new shape, therefore new volume, is 1.9, which means a mixture of ice and silicates, which is much less than was previously estimated from what's called Jacobi solution, which is a relationship between the density of the body and its rotation period. And using this Jacobi ellipsoid solution, which assumes an homogeneous body in hydrostatic equilibrium, the deduced density was 2.5, but it's not. I mean, the body is bigger, so it means that it's not Jacobi ellipsoid, and it's not homogeneous, and it's not in, probably not, possibly not in hydrostatic equilibrium. So I'm working now with some colleagues in modeling the interior of Haumea, mixing, rocky material, silicates, and ice to see if we can explain the inner structures. So not only we can derive sizes and shapes, but also have some constraints on the internal structures of those bodies. So it goes beyond just measuring size and shapes. This is an example of an occultation by Pluto's atmosphere observed from the Very Large Telescope in Chile, and you can see the drop of signal. The star is just disappearing, but not suddenly. And this gradual disappearance is caused by Pluto's atmosphere. And you see some features here. They are not caused by the Earth atmosphere, but by Pluto atmosphere. And this gives you an idea of the typical pressures. So microbar, 10 microbars, 1 microbar, and some nanobars. So it's very tenuous atmosphere, but we can see it quite clearly. And it's probably an atmosphere which is in equilibrium with the surface of Pluto, with ices being sublimated and condensed during the day, and then there is an equilibrium between the ices at the surface of Pluto and the atmosphere. And this big glacier called Sputnik Planitia is probably the very source of that atmosphere, by being heated up during the day and sublimated and then condensing again during the night. This is here a temperature profile deduced from ground-based occultation. So you can see the temperature as a function of the distance to Pluto's center, which is given here. And in color here, you have the result from the radio science occultation on board the New Horizons spacecraft, which gives some profile here. And above that level, there is not enough signal to noise to constrain the temperature profile. So not only we can see that we agree quite well with the spacecraft result, but also we have a more extended range of measurement, because there is no more measurements during that occultation, at least above that level from New Horizons. So this is the profile deduced from ground-based occultations, the pressure profile as a function of radius. And again, you see that the New Horizons results agree quite well with our general pressure profile. And contrarily to spacecraft like New Horizons, which go there only once, we are able to monitor Pluto's atmosphere over a long time, decades. Actually, this was in '88 here, and up to now meaning 2020. And you see the very big increase of surface pressure by a factor of about 3 between that epoch and now. And this is complicated. It's a big seasonal effect, which is forced by the big inclination of the big obliquity of Pluto. the inclination of its spin axis to its orbital plane, and its varying distance, big changes in heliocentric distance. And when you mix that together, then you have big variation of pressure. And they can be monitored, and now the expectation is that the atmosphere will decrease again in the next decade, and this will be possibly detected through occultation. Well, I will not insist much because it's out of the same result, but with Triton atmosphere, which looks like Pluto's atmosphere. And this is our density profile observed as a function of distance to Triton's center. And this is old results from 1989 during the radio science occultation by Voyager 2 spacecraft. And you see that, again, that's some data from the Voyager spacecraft here, and there is a nice connection between our results and the Voyager result at that time. So complementarity between ground-based observations and space observations. So as I'm not much time, I will just show you a few examples of central flashes, which are caused by the focusing of atmospheres onto Earth. So the atmosphere is like a big lens, and that big lens will focus the signal on the Earth and give rise to a spectacular, and let me show you, central flash. So you can see here a Neptune, the Triton star, and then the disappearance of the star, which lasts for about 3 minutes. And then at some point near the center of the event, you have a big jump, a big increase of signal, which is caused by that focusing of light. So it's like, so it's a bit like a microlensing in the, you know, when you're observing a star far away, which is focusing through bending of rays, general relativity, and then causing this microlensing. So the bending is not due to gravity, it's caused by refraction of the atmosphere. It's an optical effect, but it's the same kind of process. Then, without entering into the detail, these flashes are very connected, extremely sensitive to the shape of the atmosphere. So it shows, for instance, in this case of Triton atmosphere, that it is very close to a sphere. And recently, to finish, we have been observing occultation by Trojans. So they are sharing Jupiter's orbit at, say, 60 degrees in front of and behind Jupiter. And there will be a NASA mission called Lucy, which will explore 8 Trojans. And we have been starting to observe stellar occultation from the ground to prepare that mission. One of them was Hector, one Trojan called Hector. And then we could reconstruct the shape using various cores from different places in USA and Europe. And we can compare that with other models of Hector, and you can see that they agree quite well. So we'll be observing more and more occultation by Trojans to prepare the Lucy mission. And the last, more recent detection we got was by Earth crossers. So those asteroids which are crossing the Earth orbit, and there are some of them could be dangerous because they are, you know, could have an impact on Earth. And one of them was detected some years ago, 2 years ago, Phaeton. And the more recent, which is shown here, that's occultation by that Phaeton object. The other one is Apophis, and we could detect it using stellar occultation. And not only we could detect it, but we could also measure the very small change of orbit caused by an effect, which is Yarkovsky acceleration, which is basically the effect of radiation. So the photons escaping from the surface of Apophis will exert a bit of, you know, angular momentum, not angular momentum, a bit of momentum change of the body. And this is a result here in red of the stellar occultation, and show that we can detect very, very small dynamical effects on that body, and then assess the change of orbit and then assess also the hazard risk for the next encounter. Okay, so this is about my time has elapsed now. So I have more to say, but I will stop here if you want to have some questions.
Okay, thank you very much for a very clear talk, even for me that I am completely in a different field. I have several questions. I will start with one of those.
So should I go back to the? Should I leave my presentation on screen?
If you want, so you can see our faces, and in any case, you can share it again if you need some slide.
Okay. Good. So can you see me now?
Yes. So can you see us? Yeah.
Okay, good. So.
Okay, I have a question related to when you are working with the stellar occultations. Do you have a preferable type of star that you would like to use for the occultations?
No. No, because we cannot choose a star, of course, and a problem sometimes is when the star is very bright. It means that it's close by in the galaxy. It's close to us. Close meaning 50 or 100 light years. Okay, and then if it's too big, its disk will smooth out the occultation profile. But it is quite rare. Usually the star is fainter, it's magnitude 14, 15, and then the projected diameter of those stars at the object is a kilometer. And this will be the limit of resolution for us. But there is another effect called Fresnel Diffraction. And the Fresnel Diffraction is about 1 kilometer too. So for those stars, what the fundamental limitation at the end of our resolution is actually the Fresnel diffraction. Okay, so so the big stars may be a problem because but statistically they are very rare because these concern bright stars and not so many bright stars in the sky.
Yes, exactly.
There are many faint stars and few bright stars.
Yes. Okay, let's move on to another question. Reinaldo?
Thanks a lot, Bruno, for the presentation, very clear. And I have several basic questions, if you don't mind. I'm very curious because you get a precision, an accuracy of sub-kilometers scales for these objects very far, close to Pluto, right? Is it a challenge to coordinate several observations? Because I think the synchronization of the time of the observations must be extremely precise. Is it a challenge to coordinate a lot of people for doing this?
Yeah, this has been a problem for many years. So the synchronization of the timings, because if one station has a wrong timing, the cord will be shifted. And we don't know if it's because the body is distorted or because the station has a wrong timing. But I must say that the amateurs are much better than professionals to get good timing because they have what's called time box connected to GPS, and they've been developing technology of their own and sharing that knowledge between themselves. And so they know it and they have been tested that technology. And when they distribute those time boxes to different people, they know what's inside the time box. And I would say that the problem was first resolved by amateurs and then professional observatories were not so easy to solve because when you have a big telescope like VLT, they don't really care about the timing, okay? So I observed once in the 99 as an occultation by Jupiter, and that's from VLT, and the VLT station was off by 3 seconds with respect to the rest of the stations. And it was just because at VLT, nobody really cares about the timing. So it was a long process, actually, to convince everybody, including a professional, that it was important to have a good time, absolute accuracy. And I would say it looks simple, but it's not. When you look into the details, the principle is very simple, to synchronize stations. But in practice, it gets complicated because you have to transfer that time on a disk, and the computer has its own clock. You have to synchronize that internal clock to GPS, and sometimes it doesn't work. So, I mean, it's not pushing a button. It's not enough to push a button and to have a right time, but it implies technology and, software or so. And so at the end, it was not a very simple problem to solve, I agree. But now there is less and less problem with that, I would say. But sometimes it's still a problem.
Great, thanks. I have two more questions, but I'll give it the time for Juan first, and I come back.
Sure.
Hi, thank you very much for your talk. My question is regarding your theoretical studies. So the rings that you're studying, are they in a regime where they are completely gravitationally stable, or can you study from your models the formation of satellites through gravitational instability?
Yeah. Well, it turns out that, as I said, those rings, at least in the two examples we got, which is Haumea and Chariklo, both rings are from the measurement and to within error bar. They are very close to the 1 to 3 resonance, and it's pretty far away from the body, so it's close to the Roche limit. Okay, so there is a region where probably the rings are inside the Roche limit and sensitive to that resonance. But if that resonance, where it looks like they are confined, is outside the Roche limit, the disk will be evolving towards a satellite, so there will be accretion. So one important ingredient at some point, for the moment, the results of the collisional code that I showed are based on inelastic collision, but not self-gravity. So there is no, internal instabilities. But then we want to go to the self-gravity, meaning we'll have some instabilities. And then it could get more difficult to simulate that. But those rings are close to the Roche limit, meaning that good candidates for forming satellites. So it could be a route to form small satellites, which is a disk around the body. Part of the disk will migrate inside and fall onto the body. The rest of the disk will be pushed away up to the last strong resonance, which is the 1 to 3 resonance. And if this resonance is inside the Roche limit, then it can stay as a ring. And if that resonance is outside the Roche limit, that it will form satellites. And to be inside the Roche limit, the body has to rotate fast, because if it's too slow, then that resonance will be farther away and then outside the Roche limit. So the prediction of this kind of model is that the rings should preferably exist around fast rotators, so that those resonances, in particular the 1 to 3 resonance, stay inside the Roche limit to avoid the disk to accrete into satellites and disappear as such, and then form discrete bodies instead of a colliding disk.
Oh, thank you.
Hey, Nolan, would you like to make
Yes.
more questions?
So there are two people from Peru sending hello, greetings from Peru. And one person, Carlos Reyes from Lima, Peru, he's asking if is it possible undergrad students to collaborating with this research on occultations?
Yeah, of course. We are expanding. I started the occultation in the 80s, And then there was very few people observing, and my agenda is thicker and thicker, okay? My address book. And then we have some collaboration. One of my PhD students is Eric Mesa. He's from Peru. And he returned to Peru. And there was another PhD student with another colleague of mine called Miriam. And she went back to Lima also. And all these people are supposed to continue and organize occultation locally meaning at their own observatories. And if you hear about other people, we are much interested in including those people in more campaigns. And a very good example was this Chariklo observation discovery. And some of these people were from Brazil, but with small telescope, and they participated and they discovered the ring. Not as neatly and clearly as big telescopes, but it was important to confirm the reality of this ring, for instance. So my point is not to use a super big telescope, but sometimes it's more important to be there at the right moment rather than waiting for the event to go over a big telescope, okay? So the power of the method is that it can be observed by people everywhere on Earth, and the shadow, I mean, the track of the occultation goes everywhere on Earth, so there is no reason why it should go over a big telescope. So sometimes it's just impossible for amateurs because the star is too faint, but quite often they have biggish, 50 centimeter telescopes, and the camera is cheaper and cheaper. And so sometimes they can have some very interesting observations, and interesting because they're at a place where there is nobody else to observe. So yes, the answer is yes, it should be developed, and anybody interested in those campaigns should go to the Lucky page, to the Lucky Star page, and look at the predictions and use. There are a lot of services on that page. You have the prediction, you have the maps, you have the tracks on Earth. You can click on your location and see if there will be an event in the next few months at your place. So it's not just a list of events. It's also, you can play with the page and have some more information. For instance, you can say, I want to know all the events between September and October at my place that will be observable. And then the site will return you with the list. And so those people can plan the observation, and they can say, I cannot observe a star very faint, so I will select only the event with star brighter than this magnitude. And then you get a list of the star at your place brighter than a given magnitude, okay? So it's getting easy now for someone anywhere in the world to plan an observation just using this information.
Thanks a lot. I have two more basic questions from myself. Can I, Maria?
Sure.
Yeah.
Yes, go ahead.
In the studies of the atmospheres of the big bodies, the planets, so you have to translate basically the extinction into temperature and pressure to get the profile. So are the optical properties of the atmosphere well constrained by somehow other method, or you have to model composition to constrain the optical?
Well, what I showed was a disappearance of the star. It was gradual, okay? So an important point here, at least for Pluto, it's not an extinction of the star. It's a deflection of the rays. And the star is dimming because the rays are bent by refraction. So the atmosphere is acting like a lens, and that lens will defocus in some way the light from the star, and it gets fainter, not because of extinction, because the atmosphere is essentially transparent, but because of differential refraction, okay? Okay, now it's true that and then from that differential refraction, we get the density profile. Once you get the density profile, you get, the pressure profile just by hydrostatic equilibrium. And once you get the pressure and the density, you get the temperature from ideal gas equation. So you get temperature, pressure, and density. And in some cases, for instance, Titan atmosphere that I mentioned, not only you have high in the atmosphere, you have just refraction, but as you get deeper and deeper into the atmosphere of Titan, which is not the case for Pluto, you get hazes. So at some point, the star is dimming essentially due to haze absorption, which is another process. And this is very interesting because we were able to describe, to parameterize extinction as a function, for instance, of wavelength. So you could see that the Titan atmosphere was much more transparent in the infrared than it was in the blue. So there is a differential extinction, which is the same in interstellar medium. So, I mean, interstellar cloud is essentially transparent at 2 micron and it's essentially opaque in blue. So it was a way to constrain the sizes of the aerosols, I mean, the hazes, particles, okay? So it's kind of in situ measurement of those hazes, of the properties. And in terms of composition, it's true that we had to assume a composition, which in the case of Titan or Pluto, it's basically nitrogen atmosphere. So we cannot know if the atmosphere is nitrogen or methane. So you have to use some other independent information. And once we know it's nitrogen, then we can derive all those properties. And we know in the case of, I don't enter into the details, but in the case of Pluto, it's so cold that there are not so many gases at that temperature. And when you look at different gases like nitrogen or methane, only nitrogen give a plausible temperature. Otherwise, if you assume it's methane, for instance, you get a completely crazy temperature profile. So, and this was confirmed by the New Horizons probe that, Pluto's atmosphere is essentially nitrogen. So there was no problem with our assumption. It was confirmed at the end. And the same for Titan, Titan's atmosphere. The Huygens probe during the Cassini mission did confirm that the atmosphere is essentially made of nitrogen.
Thanks a lot for the clarification. And this is my last question. When you showed a study about resonances in rings, so you showed one specific example, where you had some mass anomaly of 3%. So the effect to the resonance is sensitive to this amount of anomaly, or it's any disturbance due to any amount of anomaly, small anomaly will produce the same effect in the resonance.
Well, I mean, 3% is a lot. So it's a very big mountain. So it's not very realistic. So we use 3% because we could see the effect on a reasonable amount of time during the simulation. So if you put a small mountain or crater on Chariklo, the mass anomaly will be of the order of 10 to the -4, -5. But then you get a much longer integration time. But then you can use scaling. So we are now trying to assess the effect of the scaling. So to see if the scaling predicted by theory is respected in the simulation. But an interesting point is that those mass anomalies are typical of small bodies. If you look at a planet like Saturn or Uranus, they have rings, but they are extremely axisymmetric because they are formed of gas. And their non-axisymmetric terms of the potential is extremely small. So there are basically no interaction. There is a bit of interaction and resonances between Saturn, for instance, and its rings, but it's orders of magnitude smaller in terms of relative mass. I mean, the relative mass of the mass anomaly to the mass of the body is extremely small. In the case of Saturn, it's 10 to the -11 or 10 to the -12. While for Chariklo, it can be 10 to the -4, which is 7 or 8 order of magnitude larger. And this is why resonances between the body and the ring are very weak and almost inexistent for the giant planets. They could be very important and strong because it can be shown that there's a torque, the coupling between the mass anomaly and the ring goes like the square of the mass anomaly. So if you have 10 to the minus 8 difference to the square, you have 10 to the minus 16. So there is a huge factor there, okay? And it's because it's small body. So a small body may support a mass anomaly because its gravity is weak. So a mass anomaly to 10 to the minus 4 can be supported by the surface because the gravity is very small. A giant planet is so big that any mass anomaly will be erased right away because the gravity field is so strong that you cannot maintain a mass anomaly for very long. But then it's interesting to see that what's happening and to test the theory and see what's a coupling between an irregular body and a disk. And this is what was done in the 60s by people working in galactic dynamics. They considered bars, you know, a bar at the center of the galaxy, and that bar will interact with a disk around by so-called Lindblad resonances. And this is an example where there is a strong non-axisymmetric field interacting with the galaxy, with the disk of the galaxy. Okay, so it may be that now we have another example of interaction between non-axisymmetric potential, which is a small body with big mass anomaly, and a disk around it. So it's a nice way to connect very different scales, but in some ways the same process, meaning resonances, non-axisymmetric terms, coupling and an exchange of angular momentum between the body at the center or the bar and the disk around it. So my point is, not only it can serve to explain what's going on around those small bodies, but it could be an interesting way to see what's happened in other disks like galactic disk. For instance, is a 1-to-3 resonance in galactic disk important or not? Because if it is important for Chariklo, could be interesting to see if it's important in other contexts like a galactic disk. Okay.
Thank you a lot.
Okay, thank you, Professor, very much for your talk, and thanks for everyone participating. I think we can cut the transmission and we can stay here in a Google Meet, but Richard. Okay, thank you.
Thank you.
Well, so
Thank you.
now we are